The next thing we're going to study is fluids. We're not going to spend too much time on it, just a little bit of time, make it short and sweet. First thing we'll look at is states of matter. I hope you're already familiar with this. Solids, liquids, and gases are the common phases of matter. There are some other extreme phases. Plasmas, for one, not too extreme, but this is where the electrons get removed from the atoms and you get a soup of charged particles. And there are things called a Bose-Einstein condensate. I'll just call it Bose-E, where you get these fluids with zero viscosity. Anyway, there's some other cool stuff that goes on, and we have no idea what goes on like in extreme situations in the middle of stars or neutron stars or things like that. But these are the typical ones we encounter here on Earth, and basically the only reason I want to talk about this is this last line here. Liquids and gases are both considered fluids when a scientist is talking about fluids. Typically when we hear fluids we think liquids, but it also includes gases. So whenever you're talking to somebody, you are actually excreting bodily fluids at them. So there you go. Alright, next thing we're going to look at is density. Again, I'm hoping you're somewhat familiar with this already. The symbol for density looks a lot like a P, but it's a Greek letter rho, and it is defined as the mass per unit volume. We already used this a little bit when we were looking at thermodynamics and the density of different materials, water in particular. Here's a table of densities. It's on page, I don't know what, in your book, but you'll notice the density of water that we typically used was 1 gram per cubic centimeter. But here it's listing it as 1,000. That's because the units here are kilograms per cubic meter. So kilograms you'd divide by 1,000 to get to grams, but cubic meters you'd multiply by 1,000,000, so you end up, oh, I think I got that backwards. Yeah, you multiply by 1,000,000, divide by 1,000. Anyway, that's how you get there. And a couple other interesting things. For solids, a lot of times we think about lead being as very dense, and it is quite dense, about 10 times more dense than water. But if you look at gold right here, it's even more dense than that. It's almost twice as dense as gold. Twice as dense as lead, almost 20 times as dense as water. So if you have a gallon of milk, which is mostly water, that weighs about 8 pounds. So if that gallon were made of pure gold, it would weigh 20 times as much, so 160 pounds to try to carry around that gallon of water. I mean, gold. But at least you'd be rich, right? Alright, next up, we're moving pretty quickly this time, is pressure. Pressure, again, we've kind of dealt with a little bit as far as force per unit area. We looked at pressure in the ideal gas law, but now we're going to look a little more closely at pressure in fluids. Two specific things I want you to be aware of: that pressure is equal in all directions at a given depth. Equal in all directions. So it acts not only down or up, but in every single direction. If I have a little point here, there would be pressure coming in on this location in every single direction. And the pressure in every direction is equal as long as you're at the same depth. So this cube here, it's not exactly equal. The pressure on the sides would be equal, but because the bottom is a little deeper than the top, this pressure is actually a little bit greater for that. But at a given depth, pressure is equal and it pushes in all directions. Okay, other thing I want you to know about pressure is that pressure is always perpendicular. Let me erase that. Okay. Pressure is perpendicular to the walls of the container. So if you have some kind of jar, pressure would be pushing straight out, and the walls would be pushing back straight in. That wasn't exactly straight, but you get the idea. And this would be straight up and so forth. So we don't have a parallel component to the pressure. If we did, that would cause the fluid to start moving. And so we can't have pressure in this direction, so no parallel component. All we have is the perpendicular component for pressure. All right. Oh, here's a bunch of unit conversions. We're not going to use hardly any of these units, but it's interesting to see that there are a million units of pressure. There might be more units of pressure than anything else. Maybe energy units would give it a run for its money, but we've already used atmospheres, and we've used pascals or newtons per square meter. Those ones aren't even on here. But there's pounds per square inch, often abbreviated PSI, so that's used a lot, for tire pressure and things like that. Millimeters of mercury, which is kind of a vestige from barometers, which we'll talk about later. There's another unit called torrs, named after a scientist named Torricelli. There's bars, dynes, all kinds of crazy pressure units for whatever occasion requires. Okay, now here's the equation you're probably going to be using most on your homework. We've used this equation here, pressure is force times area, but a lot of times it's easier to figure out the pressure at a given depth by using this equation here. And where it comes from is, if I want to know the pressure at this location here, a height h below the surface. So this is a little bit of a change. Normally we think of a height as above the ground or above something, but here we're talking about the height down in a fluid. So the pressure there is due to the fluid on top of that location pushing down on it. So if we think about force per unit area, we have the weight of that water, in this case it's water, but it could be any fluid, pushing down on that area. And if we rearrange our density equation, since density was mass over volume, then mass equals density times volume. So we plug this in for m, the g comes along, and we have density volume times gravitational acceleration here on Earth divided by the area, and volume is the height times the area. That's the volume of this cube. So those areas cancel out, and we're just left with this nice and tidy expression here. Density of the fluid, not the object that's in the fluid, times 9.8 times h, which is how far you are down into the fluid. And we can modify this a little bit as well. If I wanted to know the difference between, say, the pressure here and the pressure a little bit deeper here, so I'll call that H1, and this we'll call H2. And if I want to find delta P between those two depths, then that's going to be pressure at depth 2 minus the pressure at depth 1, which is going to be rho g H2 minus rho g H1. And we can factor out the rho g, and then we just have H2 minus H1. And that is just delta H. So this is kind of a nice little corollary to our equation here for finding the pressure at a given depth h. We can find the difference in the pressure at two different depths just by doing rho g delta h. Okay, now this has some interesting implications, as straightforward and simple as it seems. One of them is that the pressure doesn't depend on the volume of the water you have. It just depends on the height of the water. So this is probably an apocryphal story, but it's still a good one. It's told that Blaise Pascal, for whom the unit of pressure Pascal is named, once wanted to demonstrate this principle that the pressure in a fluid just depends on the height of the fluid. So he took a barrel, like a wine barrel or something, and he put this long tube on top, but it's really skinny. And this, according to legend, was like 10 meters tall. So pretty tall tube, right? And then he started filling this tube with water. Well, even if this tube was tiny, tiny little straw, that's still going to increase the pressure, because pressure just equals rho GH. So as long as H is increasing, it doesn't matter if this is a tiny, skinny little column of water, that's going to increase the pressure down here. And in fact, according to legend, he was able to burst the barrel by adding water up this skinny column here. And just kind of another example of that idea. If you look at a dam in a river, here is Hoover Dam. If you haven't been down there, I recommend it. It's pretty amazing. I was down there a few years back when I only had 2 of my 4 boys. And here's a picture of the back side of the dam, and you notice it goes pretty straight down. And this is the other side of the dam. You can't see it all that well, but it slopes forward like this. So what's happening is when they build dams, more or less, they look kind of like this. They get much thicker at the bottom, and that should be pretty obvious why, just from our equation that pressure equals rho GH. As H increases, because that's measured from the top of the water here, the pressure gets bigger and bigger, so the force on the wall, force per unit area, gets bigger and bigger, so you need a thicker wall. Well, that's all pretty straightforward, but kind of going back to Pascal's idea, the interesting thing is it doesn't matter how big the lake is. So you could have, here's my dam, turned kind of into a shoe shape. That's okay. You could have a tiny little lake that's just like 10 feet long versus a lake that's miles long. We'll do a little discontinuity here in the middle, and then our dam way at the end of the lake. Now my dam keeps changing shapes. Anyway, this one that's miles long would require the exact same thickness of dam as one that is just a few feet, because all that matters for the pressure down there is the height. Pretty weird. Anyway, think about it, and we can talk about it in class if you have questions. See you next time.